In this lecture, we are going to look at the radiative heat transfer and its role in Earth's climate. All of you know that the present global mean temperature is 15 degrees centigrade or 288 degrees Kelvin. So, this temperature is maintained by the radiation coming from the sun. So, we have the earth here subject to radiation from the sun, and the mean temperature of the earth is because of the balance between solar radiation absorbed and radiation emitted by earth. To space. So, this balance between the radiation absorbed from the sun and the radiation emitted to space is the balance that we are trying to understand. So, how much is the radiation coming from the sun? Now, satellites have measured this radiation quite accurately in the last 50 years, and the radiation arriving is known as the solar constant. This is the radiation normal to the sun's rays at the mean earth sun distance. You know that the earth's orbit around the sun is not a circle, it is elliptic. So, the radiation coming from the sun will vary slightly with season. So, we look at the mean earth distance. At the mean earth distance, satellite measurements show that radiation normal to sun's rays is 136 watts per meter square. So, this is an important number to remember. This is radiation arriving from the sun. Now, you might ask, can we estimate this radiation from basic principles of radiation transfer? The answer is yes. If you treat sun as a black body, then the effective temperature of the sun from measurements show this is 577 degrees Kelvin, the sun's effective black body temperature. And we know that the radius of the sun's radius is 695,508 kilometers as measured from the earth, and we know the sun earth distance, the mean distance is 149.6 into 10 to the power 6 kilometers, approximately 150 million kilometers. So, given this information about the sun's black body temperature, radius of the sun and the sun earth distance, the earth is somewhere here and the sun earth distance is given to you. So, we can estimate the radiation leaving the sun knowing its black body temperature as this into 4 pi r squared, the surface area of a sphere through which radiation is going out. That same radiation ultimately has to go past the earth And so, essentially as this radiation goes outwards, the density of the radiation will come down as 1 over r square. So, ultimately near the earth you have to divide by the surface area of this imaginary sphere whose radius is the sun earth distance. Okay. So, if you plug in this 577 degrees Kelvin and this 4 pi will cancel out of course, and the sun radius and this one, you will get a number very close to 1365. Okay. So, this quantity has been measured by satellite just outside the earth. It can also be calculated knowing the black body temperature of the sun. So, both will give the same answer. Now, let us look at what happens to now this radiation. So, let us call this S, that is the radiation coming into the earth. Now, notice that the amount of radiation that will be intercepted to the earth is S times pi r squared of the earth. Earth will intercept only the cross sectional area of the earth for pi r squared, not 4 pi r squared, pi r squared, and then a certain fraction of the radiation will be reflected and the remaining is absorbed. So, this is called the albedo. This is the essentially the hemispherical total reflectivity to sun's radiation. That is called the albedo. So, this is the quantity of the radiation absorbed. So, radiation absorbed is this by the earth. Now, at present let us pretend the earth has no atmosphere and let us assume earth is a black body, that is its emissivity is 1. So, then the radiation emitted by the earth. So, this radiation which is absorbed in the sun has to be equal to radiation emitted, and let us call the E as the effective black body temperature of the earth into 4 pi r E squared. So, in determining the heat lost from the earth, you take the entire surface area of the earth. While calculating the radiation absorbed, we only take account the cross sectional area of the earth, because only that much is intercepted from the sun. So, finally, the expression we get is S by 4, the radius of the earth is not relevant, pi cancels out, S by 4 into 1 minus alpha is equal to sigma T e to the power of 4. The quantity S by 4 will keep coming quite often in our discussion. So, I would like you to think of S by 4 as the solar radiation incident per unit surface area of the earth. So, every unit of the earth gets a radiation not S, but S by 4, because of the fact that earth has a surface area of 4 pi r squared, while the area over which it intercepts the sun's radiation is only pi r squared. So, this quantity if S is 1365, you divide by 4 is approximately 341. We will take it as 341 for our discussion. Because the actual solar constant varies between 1364 and 1365 due to the variations in sun's output. So, the actual number is somewhere between 341 and 342 in that range. Okay. So, we will take it as 341. Now, the albedo, the hemispherical toward reflected to the earth has been measured accurately by satellites in the last 20 to 30 years, and the value that we know is that it is around 0.3 or 30%. So, 30% of the radiation coming from the sun is reflected back to space. So, it is now not available for energy balance because it is gone. Okay. So, the radiation that is available to you per unit surface area is 341 into 1 minus 0.3. That is 30% radiation is reflected, 70% is absorbed, 70% of 341 is 238.7 watts of meter squared is absorbed solar radiation. So, on an annual mean basis, the earth absorbs around 238.7 watts per meter squared, and to be in equilibrium, this 238.4 watts per meter squared has to be equal to the radiation emitted by the earth. This is called the effective black body temperature of the earth. This is not the real temperature or effective radiation temperature. And so, if you substitute that 5.67, you will get TE to be around 255 Kelvin. Okay. This is equal to minus 18 degrees centigrade. So, this is not the real temperature of the earth's surface. This is the effective radiative temperature, which balances the incoming, which balances the absorbed solar radiation from the sun. Okay. Now, this is minus 18, and we know that the global mean surface temperature of the earth is plus 50 degrees centigrade. So, we would like to understand how the temperature of the surface of the earth is 33 degrees above the effective radiation temperature of the earth. So, this 15 degrees higher 33 degrees higher value. So, T surface minus T effective temperature is 33 degrees centigrade. So, we must understand what caused this temperature to go up by 33 degrees centigrade, and as all of you realize, this is because of the atmosphere of the earth. The atmosphere of the earth contains gases which are transparent by and large to sun's radiation, but they absorb the radiation emitted by the earth. And this unusual property of some of these gases is given the name the greenhouse effect. That is, the earth's atmosphere which envelops the earth behaves like the glass in a greenhouse. The glass in a greenhouse allows sun's radiation to go through into the greenhouse, but the radiation emitted by the plants and other surfaces in the greenhouse is not allowed to go through the glass. The glass is opaque to radiation emitted by the surface of the greenhouse, and that is why greenhouse is much warmer than the surroundings. So, earth is much warmer than what it would have been without any gases, is because of this unusual property of these gases, that they are almost transparent to the incoming solar radiation, but almost opaque to the radiation from the earth. And this you recall as part of a study on gas radiation, we recall that the sun's radiation is primarily in the regime 0.2 micron to 4 micron. So, gases are transparent to this wavelength, while the radiation, this is sun's radiation. Earth's radiation, as all of you recall from the Wien's displacement law, Earth is at a much lower temperature. So, the radiation it emits is between 4 micron to 100 micron, and the gases are opaque to this radiation. So, this unusual property of the gases that envelop the Earth has enabled the surface temperature of the Earth to be 33 degrees warmer than the temperature it would have had if there were no gases. Now, ironically, there are 3 gases on the Earth: nitrogen, oxygen and argon, which constitute 99.9% of the Earth's atmosphere. They are transparent to both solar and terrestrial radiation. Okay. And so, they play no role in Earth's climate. They allow radiation from the sun to go through, they allow the radiation from the Earth to also go through without absorption. There is some scattering by molecules, small amount, but as far as absorption is concerned, nitrogen, oxygen, argon have no absorption bands or very weak absorption bands in the region 0.2 micron to 4 micron. On the other hand, the minor gases like water vapor, carbon dioxide, methane, nitrous oxide, chlorofluorocarbon, they have an unusual property that they are fairly transparent to solar radiation, but have strong absorption bands absorption in the region from 4 micron to around 80 micron. They absorb very strongly. So, it is this unusual property of the minor gases. So, remember, these are the major gases which play no role, and these are the minor gases. Now, carbon dioxide amount of the atmosphere is at present around 390 parts per million. It is a very small amount. Methane is in parts per billion. Water vapor amount varies a lot depending where you are. If you are in the poles, there is hardly any water vapor. If you are in the tropics, it is of the order of 1%. So, the puzzle is how come these minor gases, which do not contribute 99.9% of the Earth's mass in the Earth's atmosphere, how come they are so effective? And the answer is because of the fact that the major gases like nitrogen, oxygen, argon do not absorb or emit any radiation. The task of controlling the Earth's climate is now in the hands of minor gases. And this is the puzzle that we need to understand fully, because a lot of people think that increase in carbon dioxide which has occurred over the last 100 years due to the burning of coal, oil and natural gas, and has increased the amount of carbon dioxide from around 280 parts per million in 1850 to 390 parts per million today. That increase of 110 parts per million is too small, and they feel it cannot affect Earth's climate, but they are wrong, because carbon dioxide has extremely strong absorption bands, which we discussed when we discussed the role of carbon dioxide in the furnaces. The absorption bands 2.7 micron, 4 micron, 15 micron, and these absorption bands absorb the Earth's radiation very effectively and prevent Earth from getting out of the heat easily. So, now let us look at what role these gases are playing. Now, if you look at the Earth's surface temperature, it is 288 Kelvin, and we assume black body, we can estimate that sigma Ts per 4 will be 390 watts a meter squared. And we know from satellite measurement that at the top of the atmosphere, the radiation going out is approximately 238 watts a meter square, which is balancing the absorbed solar radiation around 238. Okay. So, the difference between 390, which is emitted at Earth's surface, minus 238, which is going out, 152 watts a meter square, is really what we call the greenhouse effect. So, Earth is emitting 390 watts a meter squared, but all that radiation emitted Earth is not going to space, because in between is sitting water vapor, carbon dioxide and methane, and they are trapping this radiation, absorbing it and emitting it back to the Earth as well as to space. And these gases are at a lower temperature than the Earth's surface. So, ultimately the radiation that the Earth is able to send to space is much lower than what is emitted by the Earth's surface. And this is what causes the temperature of the Earth to go up. And of this 152 watts a meter squared that is being absorbed by water vapor, CO2 and methane, the most important is water vapor. It contributes about 60% to this trapping, and about 25% is on account of carbon dioxide, and about 15% is on account of clouds. Clouds also trap radiation. There is a cloud sitting in the atmosphere. It will absorb the Earth's radiation and re-emit it at a lower temperature. So, clouds also contribute to greenhouse effect. So, all the three combined total effect is around 152 watts a meter square. Now, can we model this phenomena in a simple way? So, we will address the issue by doing a very simple model of the Earth's atmosphere. Earth's atmosphere is fairly complicated. The temperature varies from 288 at the Earth's surface to around 200 Kelvin at the tropopause, which is the end of the troposphere. I forgot ozone. Ozone is also a gas which absorbs radiation from the Earth. So, this is around 288 and this is around 200 Kelvin, and then in the stratosphere temperature starts rising again because of ozone absorption. And so, if you want to model this phenomena accurately, you have to solve the full equation in the from the surface top of the atmosphere. You have to solve the full equation under radiative equilibrium, which we will take up in the next lecture. It is similar to the problem we solved between two parallel plates, but we have to slightly modify the derivation. But before we get into that, we would like to do a simple analysis which simplifies the problem substantially, so that you get some insight into what is happening in the Earth's atmosphere. To do that, we will treat the Earth's surface as one layer, and the atmosphere as one layer. Okay. Now, this is not a good approximation. Atmosphere cannot be treated as one thin sheet of glass, but we will do that. So, we will assume that this thin sheet emits radiation upwards and downwards, and the radiation coming from the sun is of course S by 4. And what is reflected is alpha into S by 4. So, what is absorbed is the difference between these two, and the Earth's atmosphere absorbs some radiation from the sun. So, A is the absorbed. So, what reaches the Earth's surface is S by 4 into 1 minus alpha minus A. And we assume that nothing is absorbed by the Earth's surface, and the Earth's surface emits sigma T S to the power of 4, and we do a simple radiation balance. This is strictly not correct, because there is also energy transferred from the Earth's surface to the atmosphere by evaporation, by what is called sensible heat flux, the normal heat transfer, convective heat transfer that we learn in engineering, but we will neglect that at this point. So, if we do a simple radiation balance, so at the top of the atmosphere here, you can see clearly that what is absorbed at the top of the atmosphere is this, and what is coming is the emission from the atmosphere, and transmission, which is 1 minus absorption, which is same as 1 minus emission, times the surface. So, here is a radiation coming from atmosphere, from the surface transmitted through the atmosphere. This is the balance for the top of the atmosphere. At the Earth's surface now, we rewrite at top of the atmosphere, we will rewrite it S by 4 into 1 minus alpha is equal to what is emitted by the atmosphere and what is transmitted through the atmosphere. Okay. Then at the Earth's surface, radiation coming in is after reflection and absorption by the atmosphere, and plus we must also think of the radiation emitted downward by the radiation that is emitted downward by the atmosphere, which is absorbed by the Earth's surface, and this has to be equal to what is emitted by the Earth's surface. Okay. So, this balance is at the top between the solar radiation absorbed and the heat lost to space from the atmosphere and the Earth's surface, and at the Earth's surface the balance is between radiation coming to the Earth's surface from the sun after reflection absorption by the atmosphere and radiation coming down from the atmosphere towards the Earth's surface, and that is equal to what is emitted by the Earth's surface. We can also do a balance. So, this is at surface. These two equations are enough for us, but just for completeness, we can also do a balance for the atmosphere. For the atmosphere, what is absorbed is the sun's radiation, and what is absorbed is from the Earth's surface, and these two has to be equal to emission in both direction by the Earth's atmosphere. We do not need this really, because from these two you can get this equation. You can see clearly that if I subtract this from this, you will get this answer. Okay? You can easily verify that. So, we take the first two equations and solve for surface temperature and atmospheric temperature. Very easily you can solve. So, if you solve it, you will get T_s to the power of 4 is equal to so, this is expression for Ts and expression for Ta, atmospheric temperature will be so, there is a useful result here which clearly shows the factors which control the surface temperature of the earth and of the atmosphere. Of course, depends on the incoming radiation as before, depends on how much is reflected by the earth atmosphere system, what is absorbed by the atmosphere. You can see here, as more and more radiation is absorbed by the earth's atmosphere, temperature of the earth will go down, surface temperature. And as the emissivity of the atmosphere goes up, this quantity will go down, the temperature will increase. So, that is what is happening in the last 100 years on account of the increase in carbon dioxide by around 110 parts per million. The emissivity of the atmosphere has gone up slightly, and that is enough to increase the temperature of the earth by 0.1, 0.2 degrees centigrade. Now, let us put in some numbers to see what kind of results we will get. Before I do that, I want you to look at special cases so that you understand the limiting expressions here. Suppose atmosphere does not exist, then the emissivity of the atmosphere is 0 and absorption of the atmosphere also will be 0, and you will get back the result which we got earlier, which is that okay. So, if you say that the this 0, okay, I am sorry that 2 numbers, I am sorry. So, we make this 0 and this 0, this 2 will cancel out. So, we will get this result, which is standard result, which is same as what we got earlier. On the other hand, if the emissivity of the atmosphere is 1, the atmosphere behaves like a black body, but the solar absorption is 0, okay, then you will get this quantity to be so, this number for alpha of 0.3 we already calculated is 255 Kelvin, okay. While this one, where the atmosphere behaves like a black body, but does not absorb sun's radiation, you will get a very high value of 302. So, you must understand the difference here. This is in the absence of the atmosphere, we get the effective radiating temperature of Earth is 255 Kelvin, which we already got. Now, if you have atmosphere which is a perfect absorber of the Earth's radiation, that emissivity is 1, then temperature shoots up to well above the measured surface temperature of the Earth, okay. and so you get a number close to instead of 288, we are getting around 14.5 degrees higher. Okay. But the emissivity of the Earth's atmosphere is not 1, it is more around 0.6 and so on. So, you put that kind of number, you will get 288. Okay. So, let us now put the number. Suppose you take albedo as 0.3, solar absorptivity which is typically around 0.2, and S as 1365 watts a meter squared, and we ask what is the so you will get T h to the power of 4 is equal to S by 4 is 1365. This alpha is 0.3, 1 to 0.7, 0.7, 1.4, 1.4, 1.2 here. Divided by 4 sigma into 2 minus epsilon A. So, if the epsilon A is chosen around 0.6, you will get a number which is around 288 Kelvin. Now, of course, we cannot with great surety estimate the emissivity of the atmosphere. Anyway, this model is very simple. It has neglected evaporative heat transfer of the Earth's surface. So, you will not expect it to give you a very good answer, but this model gives you some idea of the role played by the emissivity of the Earth's atmosphere in Earth's climate. If the emissivity was 1, the temperature would have been around 14.5 degree larger. So, that is. Now, let us try to understand the sensitivity of this result. It is good to get a feel for how sensitive the result is to small changes in temperature. You now differentiate this and calculate what is the change in temperature to small changes in the emissivity of the atmosphere. So, we will get the following result. One by 4 into 2 minus epsilon A. Okay. So, you put a typical value epsilon A around 0.6, then you will find, and typical temperature 288, you will find that in the present climate this quantity is around 72. So, what this means is, if the emissivity of the atmosphere goes up by just 0.01, the temperature of the Earth will increase by 0.72. So, this is what this model shows very beautifully, that is, it takes a very small change in the emissivity of the atmosphere to increase the Earth's surface temperature by around 0.7 degrees centigrade. And interestingly, over the last 100 years, the mean temperature of the Earth has gone up by 0.7 degree. And so, the emissivity has changed by around 0.01, not only due to the increase in carbon dioxide, but as the temperature went up due to thermodynamics and the Clapeyron equation, the water vapor also went up along with it. And all these are contributed to the increase in emissivity of the atmosphere by around 0.01, and notice that this is a very small change. So, it is not something which you can measure easily. a change in emissivity of 0.01 is not going to be very easy to measure, and so that must be kept in mind before we look at the answer in more detail. Okay. So, this is the role of emissivity, very sensitive role emissivity playing. We can also look at the effects of other parameters, so that we get some appreciation of the role played, for example, due to changes in solar absorptivity. So, you can calculate how much the temperature is changing in response to changes in solar absorptivity of the earth, and you will get minus 1 by 4 into 2 minus epsilon A by 1 minus 2 into 1 minus alpha minus A. So, if you estimate this for typical conditions that prevail today, you will see that for change in absorptivity of a change observed at 0.01, okay. It is a very small change. You will say delta A increases by 0.01, the absorptivity of the atmospheric layer. Then according to this estimate, the surface temperature will, I will use a common symbol here, if the absorptivity goes up 0.01, very small change, the temperature will go down by 2.5 Kelvin. So, there is a big change. Again, notice how sensitive the Earth's atmosphere is to small changes in the solar absorptivity of the Earth. I am sorry, let me correct a little bit, I am sorry. Surface temperature, if the goes down by, I am sorry, 0.06 degrees Kelvin. Now, similarly, you can calculate the effect of changes in albedo. If albedo goes up by 0.01, the temperature will drop a little bit faster, 0.12 Kelvin. Now, what it means is that this also is a very small change in albedo of the Earth that can be occurring due to changes in cloud, or it could be changes in ice or snow cover. So, if all these changes the reflectivity of the Earth atmosphere system by just 0.01, from let us say 30 it goes 31, the temperature drops by 0.12 Kelvin. And these changes have occurred. For example, during a large volcanic eruption, the absorptivity of the atmosphere can go up by 0.01, it has happened, or even more, okay. And that can cause a fairly large change, large cooling of the Earth's surface. So, we have historical data showing that whenever there was a major volcanic eruption on the Earth, the temperature of the Earth cooled by around 0.1, 0.2 degrees Kelvin. That means, the absorptivity went up by around 0.03, 0.04. Similarly, small changes in the Earth's albedo, that is reflectivity, on account of changes in cloud or changes in ice or snow cover can cause cooling. Okay. So, we look at the past climate of the Earth, we do see Earth's climate fluctuating by around half degree Kelvin, and all these can be easily related to either changes in the Earth's absorptivity due to volcanic eruption, or changes in Earth's albedo due to changes in clouds or ice cover, or the third factor we have not discussed, which is the changes in temperature due to changes in incoming solar radiation. So, solar radiation need not remain a constant, it can fluctuate due to changes in solar activity or changes in Earth's geometry. Both these can cause some changes in S, and that can also cause some amount of cooling or warming of the Earth. So, all these factors have played a role in the Earth's past, but our interest at present is in the Earth's future. So, if you look at the temperature changes occurred in the last 100 years of the order of 0.7 degrees Kelvin, we can attribute definitely to changes in emissivity and absorptivity of the Earth's atmosphere, primarily caused by an increase in carbon dioxide, and then later which caused the water vapor to go up, and that also contributed to the increased emissivity. And the real challenge that we now face is about what is going to happen in the next 100 years till 2100, and if we continue to burn coal, oil and natural gas, the carbon dioxide, which is now approaching 400 parts per million, will go up to something like 600 or even 700 parts per million, and this will cause much larger increase in Earth's temperature. So, this is a sufficiently serious long term problem that we need to worry about its consequence of the future of the Earth. Now, the reason why we need to worry about it is, if you look at the Earth's past climate, it has fluctuated between ice ages, when Earth's temperature was 4-5 degrees lower than the present, to warm periods when the ice cover was very low and temperature of Earth was a couple of degrees warmer than present. So, these kind of fluctuations have occurred. So, it is important to remember that the Earth's climate is not stable. It can go up or go down on account of natural fluctuations or human induced fluctuations. In the past, human being did not play much role. The major role was played by natural perturbations like the volcanic eruption or changes in the sun's output. But today, the dominant perturbation to the Earth's atmosphere is coming from human being and their emission of large amount of carbon dioxide due to burning of oil, coal and natural gas. So, this simple model illustrates clearly the role of all the three quantities. So, we are able to now summarize that small changes in the incoming solar radiation or the Earth's albedo or solar absorptivity or emissivity can cause large changes in surface temperature. So, the Earth's climate is sensitive to changes in the incoming solar radiation or changes in the reflectivity of the Earth, albedo, or the solar absorptivity or the emissivity of the atmosphere. And hence, it is necessary now to carefully monitor the Earth's climate to understand what role is being played by which parameter. Now, the reason why we are concerned about is the example of Venus. Venus is a planet very similar to Earth in terms of size and the initial composition. The amount of carbon dioxide in Venus, for example, if you take all the carbon dioxide in the surface, in the rocks and in the atmosphere, the total amount of carbon dioxide the Venus has is no different from that on Earth. But on Earth, all the carbon dioxide is stored in the rocks as calcium carbonate. Only a small amount of carbon dioxide is present in the atmosphere. In Venus, it is exactly the opposite. Most of the carbon dioxide has come out of the rocks, is now in the atmosphere. For example, the Venus composition contains 96% carbon dioxide, while Earth the composition is around 4%. So, the Earth has much lower amount of CO2 in the atmosphere than Venus. Because of the strong presence of carbon dioxide in Venus, the surface temperature of Venus is close to 720 degrees Kelvin, while that of the Earth is only. So, this shows clearly the important role of the greenhouse effect on Venus. Venus and Earth started out with the same temperature, but on Venus all the water in the ocean evaporated, went into the atmosphere, caused a very large greenhouse effect, increased the temperature of the surface of Venus by 100 to 200 degrees Kelvin. That caused all the carbon dioxide which is in the rocks as calcium carbonate to come out as carbon dioxide, and as the carbon dioxide amount in the Venus atmosphere went on increasing, the temperature of the Venus went on increasing to around 720 degrees Kelvin. We do not fully understand all that happened in the past in Venus, which caused it to come to the present hot house or the very warm hot conditions. But we know that the greenhouse effect played an important role, that all the water which was originally in the liquid form on the Venus surface, it is all boiled off, went to the atmosphere, caused large warming, and that ultimately caused chemical reactions at the Venus surface, which converted calcium carbonate to calcium oxide and carbon dioxide. And this carbon dioxide is a very powerful greenhouse gas, so caused more warming, and this went on till the temperature of Venus reached 720 degrees Kelvin. So, we have to worry about whether by burning coal, oil and gas in the Earth's atmosphere, whether we will slowly over a period of hundreds of years increase the temperature of the Earth so much that a lot of carbon dioxide which is stored in the oceans and in the land in the soil and in the vegetation will all start coming out and increase the carbon dioxide concentration in the atmosphere by a large margin, and will cause Earth to rapidly warm like Venus. So, that is a issue which has to be looked at critically. The prediction is that if you continue to burn coal, oil and natural gas at the rate which we are doing now, the Earth's temperature may go by around 5 degrees or even more in the next 100 years. That will bring more carbon dioxide into the atmosphere, and in the subsequent centuries Earth can warm more and more. So, this is a serious issue and demands very detailed analysis, and we will look at some more examples of the role that radiation plays in Earth's climate in the subsequent lectures. The analysis we gave today is a very simple one, single layer model which is very limited. We have to account for the variation of the temperature with height in the Earth's atmosphere, and that we will take up in the next lecture and show how that ultimately controls the vertical profile of temperature in the Earth's atmosphere. And so, that analysis will require solving the full radiative transfer equation, and that is similar to what we did for two parallel plates, and that is issue we will take up in the next lecture.